Hello, I am Jae-hee Lee, the head instructor of Lee's Science Academy. LSA. Today, following our study on the 4 basic operations of natural numbers in the last class, we will learn about the closure and openness of operations on natural numbers. Here are the main topics for today's lecture. We will explore how to represent numbers using letters instead of numbers as a method of expression, and examine the meaning of the closure and openness of an operation. We will learn about the method of proof in the deductive system of mathematics, prove mathematically that the addition operation is closed among the 4 basic operations of natural numbers, and prove through logical thinking that the multiplication operation is closed. Before doing the proof, let's define literal numbers. Numbers like 1, 2, 3 are symbols that express numbers with clearly defined magnitudes, such as 1, 2, 3. Then when do we use literal numbers? If a number exists, but its magnitude is not yet determined, or if the magnitude is determined, but we do not want to reveal it, how can we express that number? In such cases, mathematicians use letters instead of numbers as symbols to express numbers. It means a letter expressing a number, and a number made of letters, so it is called a literal number. By convention, lowercase English alphabets are mainly used. When expressing numbers with letters, the letter used becomes a literal number, not just a letter, so it must be distinguished from a normal letter. A, B, C are English alphabets and letters, but when we say literal numbers, A, B, C, the A, B, and C here are not alphabets but symbols expressing numbers. You can distinguish them, right? This time, let's define constants among literal numbers. Among literal numbers, a literal number expressing a number with a fixed magnitude is called a constant. There are numbers whose magnitudes are fixed, but we do not yet know their exact magnitude. Such numbers are specifically distinguished among constants as unknowns, meaning we do not know the number. Also, there are variables distinguished from unknowns. If a number exists, but its magnitude has not yet been determined, and its magnitude can be determined in various ways later, the literal number expressing such an undetermined number is called a variable, meaning a changing number. By convention, variables are mainly represented by the lowercase alphabets X, Y, Z. Let's look at an example. Science report card of grade 3, class 1 is expressed as literal numbers, and A express the physics score and B express the chemistry score, then the literal numbers A and B do not have a determined value until a specific student is chosen. Therefore, the literal numbers A and B at this time are variables for the score of student number 1. If we say that the literal numbers P and Q express physics score and chemistry score, then the literal numbers P and Q at this time are constants. This is because student number 1's science scores are already determined. If student number 1's physics score is 95, but we do not know the chemistry score Q, the literal number Q is a constant, but it is an unknown. This unknown can be assigned a value, like 85, if we provide a single condition, such as the chemistry score is 10 points lower than the physics score. As we will learn later, an expression containing an unknown is called an equation. Finding the value of the unknown is called solving the equation, and the value found is called the root. The general definition of the closure of an operation is that when the number obtained by performing a given operation on a given set is an element of the given set, the operation is defined as being closed under the given set. It is called closed because the result of the operation is trapped within the set. When an operation is open, it means the operation is not closed, meaning the operation result is not an element of the set. Applying the law of excluded middle to the closure and openness of operations, there is no third case other than being closed or open. Determining in advance whether an operation is closed or open allows us to judge what properties the set of numbers on which the operation is performed has, or, in other words, what elements it contains. An operation requires a set of numbers to be operated on as a premise, and the operation must be performed within that number set. If the operation is not closed under the set of numbers being operated on, the calculated number might not be included in the number set, so you cannot perform the operation with peace of mind and would have to check the result every time. If the numbers are clearly revealed, you could check the result every time and proceed in the right direction, but if the numbers are given as literal numbers and their magnitudes are unknown, there are cases where the operation itself cannot be performed. Only when the operation is closed under a given set is there absolutely no possibility that the operation result will be outside the number set, allowing you to calculate freely with peace of mind. Let's look specifically at the closure of the four basic operations on natural numbers. In the set of natural numbers, addition and multiplication are both closed, and subtraction and division are open. Closure must be strictly proven, but since being open is a case of negation, you only need to show one example where it is not closed. Such an example of negation is called a counterexample. As a counterexample of subtraction, the operation value of natural number 5 minus natural number 6 is minus 1, which is not an element of the set of natural numbers, so it is not closed. The letter N is a symbol representing the set of natural numbers, and the symbol with a slash through a fork shape is a symbol expressing is not an element of a given set, as you will learn in sets. Then the fork symbol without slash would express is an element of a given set. As a counterexample of division, natural number 6 divided by natural number 7 is approximately 0.86, which is also not an element of the set of natural numbers, so it is not closed. Before we do the proof, let's talk a little bit about proofs first. Since we learn mathematics as a tool for studying, when we first learn mathematical knowledge, if we prove it once and understand its content, from then on we can freely use the results without doubting or hesitating about that content. When you learn it for the first time, I hope you make it a habit to prove it yourself at least once. Mathematics is composed of a deductive system with a conditional statement structure of if P, then Q, based on axioms and definitions. The deductive system takes a form like if P, then Q. The very first proposition, Pn plus 1, is called an axiom or a base assumption, and it is accepted as true without proof. Since the deductive structure is if Pn plus 1 then Pn, if Pn plus 1 is true, all propositions down to Q become true according to the deductive structure. Do you understand? In mathematics, a proposition proven after the base assumption is called a theorem. All proofs in mathematics start from definitions and axioms and must be proven from the very first step, but in practice, for convenience, we use definitions and theorems to start proving from an intermediate step. What we need to prove here is the closure of the addition rule, that the result of adding any natural numbers is a natural number. There are induction and deduction methods for proving propositions. Induction is a method that judges it to be correct and considers it proven if there are no cases where it is wrong based on experience. When proving closure, If you actually add two natural numbers and show that 3 plus 4 is 7, which becomes a natural number, or 7 plus 9 is 16, which becomes a natural number, you have proven it by induction. No matter how you add any natural numbers, you never get a non-natural number by adding natural numbers, so since there are no counterexamples, we accept that it is a natural number. For more details on induction, please refer to the recommended lecture below. Proving a proposition by induction is generally a valid proof, but for mathematics, which does not allow exceptions, it must be proven by deduction. In mathematics, which has a 100% abstract deductive system, proving by induction and ending the proof leaves something to be desired. The principle is that proofs in mathematics should be done by deduction. We confirmed this in the induction proof, but the commutative law seems so obvious that it can almost be accepted intuitively. Proving something that seems obvious deductively can be unfamiliar and difficult, but if you practice it a few times, you will quickly get used to it, and in the process of doing the proof, you will be able to understand the mathematical system better. I will do it directly so that proving is not unfamiliar. The core of the proof is knowing what a natural number is, since we have to prove that the operation value is a natural number. Since we know that natural numbers are numbers that increase by 1, we just need to show that the result is such a number. For the properties of natural numbers, please refer to the recommended lecture in the description box. We will deductively prove that the addition of natural numbers is closed under the set of natural numbers in operations within the set of natural numbers. Let's set the universal set of operations, U, as the set of natural numbers. Then arbitrary natural numbers a and b to be operated on become elements of the set of natural numbers. According to the definition of natural numbers, a can be rewritten as adding 1a times. B can also be rewritten as adding 1b times. If we set the operation value of adding a and b as the literal number c, showing that c becomes an element of the set of natural numbers completes the proof. Let's do the proof. For the left-hand side, a plus b, we can rewrite it using the expression of the definition, since identical things are identical. Since the commutative and associative laws hold for addition, we can remove the parentheses and group the whole thing into one. Then, the total number of ones added in the whole is c. Therefore, the entire number can be expressed by the literal number c, which becomes an element of the set of natural numbers. Since this is equal to the right-hand side, the proof is complete. In mathematics, when a proof is completed, we write QED to indicate that the proof is finished. For convenience, it is also written in lowercase letters. This time we will prove that subtraction is open by showing a counterexample. Literal numbers a and b are the arbitrary natural numbers shown earlier. Let's assume one of the two numbers is greater than the other by 2. Here we'll say a is the larger number. Then, according to the definition of natural numbers, we rewrite the two numbers as the addition of ones. A has 2 more. For the subtraction operation A minus B, we just need to take away 1's equal to B from A, leaving 2, which makes 2. Since 2 is a natural number, it is closed. However, for the subtraction operation B minus A, there are more pieces to take away, so the operation cannot proceed. It becomes impossible. Therefore, subtraction in this case is not closed. Thus, it proves that subtraction is not closed under the set of natural numbers. When we create negative numbers and complete integers later, we can complete this operation as minus 2. Did you understand well? This time, we will prove the proposition that the multiplication of natural numbers is closed under the set of natural numbers in operations within the set of natural numbers. Like the closure of addition, multiplication could also be proven with elements and formulas, but this time, let's try a method of proving the conclusion deductively through logical thinking. Multiplication of natural numbers is the repeated addition of natural numbers according to the definition of multiplication, so it is adding multiple times. Since the addition of natural numbers is closed under the set of natural numbers, the result of the very first addition is closed, so it is a natural number. If we do a second addition with the first addition value of natural numbers, of course addition is closed, so it becomes a natural number again. In this way, if you repeatedly add as many times as the multiplying number, you obtain all natural numbers, so we can prove through logical thinking that multiplication is closed under the set of natural numbers. You understand, right? Let's summarize today's lecture. Today we studied that in an operation within a given number set, the closure of an operation means that the operation value must be an element of the given number set, and we also studied that only when the operation is closed can we safely and freely perform operations on literal numbers. We understood that in the 4 basic operations in the set of natural numbers, addition and multiplication are closed and subtraction and division are open. Next time, we will look into the operation rules contained in the operations of natural numbers. This concludes today's lecture. Thank you.